reactions. So the presentation by Braden Weight, will go over the iron porphyrin.
Oh, thanks for the introduction. Yeah, so I'll be discussing some preliminary data on a chlorite decomposition reaction to produce, say, molecular oxygen and chlorite ion. So there's a class of enzymes, chlorite dismutases, that are known to participate in such reactions, such decompositions of chlorite. So, interesting to note, molecular oxygen is somewhat difficult to create synthetically. So it's very cool to see something in nature that catalyzes this reaction. So that's a very important reason why we should be looking at this.
It's very hard to hear you.
But the chlorite ion itself is a negative ion, but throughout the simulations, I've explored different charges for different things as well. Okay, so in the actual enzyme itself, obviously it's a very complex system where just a small part of it, usually called the pocket, enzyme pocket, which houses a heme macrocycle, so an iron center macrocycle with 4 adjacent nitrogens, and usually some axial ligand. In this case, it's an imidazole connected with the long arm. But the enzyme itself obviously is composed of thousands of atoms, and we cannot obviously do that using density functional theory or any ad initio methods. So what we're considering here is a very simplified version of this. So we just have the macrocycle itself, the iron in the center connected to an imidazole linkage with a part of an arm. And to kind of make it a little bit more realistic, I've fixed these 2 carbon atoms in space in all 3 dimensions, such that this imidazole is a little bit more rigid than it would be if I was to relax those degrees of freedom. Because this carbon atom itself is connected to a long chain here, which would offer a little bit of rigidity for that line. And in addition, there's stuff above that I'm neglecting as well that will probably make big consequences in the overall reaction in reality. But again, we're using a very simplified model here, so we just want to model the reaction at the surface, at least in parts. And that'll make more sense when I get to it. So, what reaction is happening? So we're looking at chloride, so oxygen bonded to a chlorine bonded to another oxygen, usually in a single anionic form. So it's hypothesized and also seen in experiment that the oxygen, or one of the oxygens, will bind to the iron, and then we'll go into some transition state, possibly one where you have a hypochlorite ion stabilized by some nearby amino acid chains, mainly an arginine that's kind of sitting above the surface. But that has not been necessarily seen in experiments to my knowledge. And then, also interesting fact, it produces a peroxide linkage, so an oxygen-oxygen bond that has been seen in experiment. And then it would undergo another last step to produce molecular oxygen and chloride. So we're interested to know if this reaction can take place, or which direction this goes, if it's like a homolytic bond cleavage event or a heterolytic bond cleavage event. This is unknown and is the main instigation for doing this. Okay, so here's my one methodology slide. So we're using VAP software to calculate all of these equations. So we're using the CHEM single particle equation. And so if somebody has questions, I can come in. Oh yeah, interesting to note there's an error in my paper write-up. There should be a square marking here, but there is not. But so I've calculated optimized these structures separately, and I've tabulated them. So if you look at the total energies, which is most important here, chlorite likes negative charges. So the negative total energy implies that it's a more stable structure, of course, and so if you have more negative, it's kind of implied that it's a more stable structure. So like I said earlier, chlorite here is known to be in a single anionic form usually, but as you can see, it's not the lowest number here. This could be an artifact of the results from the DOT. We could move to higher level results, and this may change. So it's important to note that we could use higher level methods at the time, and I will probably be doing, I actually have some calculations right now doing optimizations for higher level theory. One more thing to note about this is the fourth column here, the magnetization changes, of course, when you have different numbers of electrons. We'll come back to that in a second when we talk about those things. So here's the density of states for each of the structures. So you can see that the bands themselves are pretty distinct, separated by, for the positive ones, separated by many electron volts difference. So more interesting to note, the ones that should be look a little bit more reasonable. So the absorption spectra are shown here, and for chlorite, this one we see, because the occupations are so close, we see a large bump in the absorption energy because it's occupied next to unoccupied, so that's discussed in a previous presentation. So, well, we can calculate the just the macrocycle by itself, and so we get a structure that looks something like this. And so you have a partially spin up, partially spin down occupied state. Since we do spin polarized calculations, we have the ability to do that. And if you analyze this absorption spectra, you can pick out some peaks that are indicative of say, porphyrin range, but I haven't done too much analysis into that for this purpose. Now we can look at the combined structures. So, like I said, there's reaction pathways that are hypothesized and some seen in experiments. So this first one on the left, we just have an oxygen binding the hypochlorite and the iron, and so that's shown here. And then the next stage, which has been seen in experiments, that peroxy linkage, we have that shown here, and another state as well. We have shown here. This is maybe the hypothesized transition state. So the hypochlorite may be sitting above this macrocycle, stabilized maybe by a nearby arginine charged amino acid. And absorption spectrum as well. But so more interestingly, we can run dynamics to shoot a chloride ion at the iron, say at different angles, at different velocities, to simulate how this reaction might progress in nature. So the potential energy surface, of course, is very complex, but knowing picking a vector approach and choosing different velocities, you can kind of estimate the activation barrier for this reaction to occur roughly. And so some observables you can look at is the bond distances, of course, of different atoms to see if things are participating in bonds as evolving in time, and also charge and partial charge density, the HOMO and the LUMO orbitals visualized as a progression of time and their localization. Okay, so here is the first video. So the chlorite ion is approaching here at 60-degree incline to the plane, in the same direction as it would in real life, or from the same plane as it would in real life, coming between the two carboxylic groups. So that's where the pocket opens up to the outside world. So you can see kind of the artificial bond, of course, but the iron has kind of snatched that oxygen from the chloride, and the chloride has some residual momentum, of course, so it goes off, but retains this oxygen. So it's, this is the first step in the hypothesized reaction. And so now this is where the hypochlorite might be stabilized sterically or coulombically by a nearby charged species, and then it may flip around to create that peroxy linkage that is also hypothesized. So looking at this from not a nature example, so looking at it in steps, right? So if we've modeled this first step, now we can think, so we can take that product and maybe shoot it in the reverse direction or from other angles as well to get the second step. So kind of eliminating maybe the transition state structure itself, just looking at what could happen at step 1 and step 2. And so here is another one that didn't work out, 60 degrees again. So here we have 60 degrees again. It did not work out because this one was at a higher velocity. And so it's kind of a double-edged sword. You can't have it too high velocity because it'll bounce off and possibly break the bond in and of itself, but this oxygen won't attach. But too low, it'll bounce back or reflect off of the potential energy surface. So it's a real kind of fine-tuning to get this right. And so here is a very preliminary result of say HOMO and LUMO orbitals as a progression of time. So of course this is very staggered because I only took every 10 steps. I calculated the electronic structure and computed the charge density. So I could make this much smoother if I was to look at every step in multiple dynamics. But interesting because some of the, and you can see this in the paper, I think maybe a little bit better. Some of the charge densities look very nice, but they jump very quickly over a 10-step region. So this is really not that informational if I take that many steps. And also the time step in the molecular dynamics should be reduced. Currently it's at 1 femtosecond. For reaction type processes, this should most likely be reduced to gain better electronic convergence between steps. This is my main. It's the same thing. So, so like I said earlier, this is more or less a meaningless plot, but you can make a lot of interesting plots. So Melissa had temperature and total energy. Here I'm computing bond distance between the iron and the oxygen nearest, and the iron and the chlorine. And so just from this, you don't have to look at any videos. You can see that a reaction took place as these two are initially equidistant. And this one separates, and this one has some oscillatory bond. So conclusions, we successfully modeled the first stage, not quantitatively, but very qualitatively. And so now we can restart simulations with hypochlorite coming back in, say from another direction, to try and form that peroxy bond that we're interested to see. And so we can do all this at higher level if we would like, but qualitatively it seems to agree with what we think, except for the total energies in the anionic systems by themselves. So to sort out the possibility of spin flip processes is also very interesting. And very interesting for this reaction, because in any transition metals, of course, you can go high spin, low spin, given things can happen. So you can use non-collinear spin calculations, which is much more expensive, but it allows for an interesting magnetization vector as a time-dependent magnetization vector, which might be very interesting to look at as well. So that concludes my talk. Any questions?
Okay, let's thank Braden.
Go back to the chloride slide where you were showing the absolute energies. Sorry, slide numbers are always useful. Yeah, this. How are you determining those energies on the left with chloride? Oxidation state.
That's a really good question. Well, the total energy of the system is obviously given as a result of using these simulation packages, the software VAST. But the total energy is calculated different ways. When DFT, of course, is calculated as a function of the density. So it's just a contribution of all the different terms, so potential terms.
But what molecules specifically are you modeling? You're just modeling the ones on the left?
Oh, sorry. Yeah. So this system, maybe I should bold separate this. I have two lines here to separate, but this system contains 1, 2, 3 values, and then I have a new system here.
Yeah, that's the chloride dismutase. But when you're modeling it, you're setting it up as a chloride with 2 oxygen bonds, and then you're just setting the total number of electrons.
Yes, that's exactly it.
Does that give you meaningful numbers?
So you may, let me reformulate the question. Do you have any suspicion in this number? And if you do, what are the possible mechanisms that can affect the precision of these numbers?
Well, so these calculations are done in vacuum. So I think this could be one thing. Stabilization could occur between molecules. That's what you're getting at.
Would a free electron have any energy contribution to this number? Does adding an electron intrinsically change the number, regardless of the state of the system? If you're just adding in an electron.
I mean, there's completely
Completely non-bound, would it change the value for your total energy? Does a non-bound electron have any energy?
should.
Okay.
So you're saying normalization to compare it better. That's what you're, okay, I see what you mean.
The electron has to come from somewhere, right? So if you add an electron directly to any system, the total energy is always going to go down. Always going to become more negative. And that's what you're seeing here, right? As you reduce, the number always goes down. Doesn't matter what the orbital energies are, because even if the orbital energy would be too high, the electron will just float around, not bound to anything. And the electron energy will still become more negative. So that electron has to come from somewhere. So you need to balance it out by having a corresponding oxidation somewhere else. Model of oxidants. So one way to do that would be to say, to correlate one of these ClO2, say the ClO2 minus, to the change between the CLD, the chloride dismutase going from -1 to 0, and the -1 to -2 over here. And then you can see what the total energy change is when you do that electron transfer. And that can give you a good idea of what's going on. Typically, you would use ferrocene for this, because if you reference to ferrocene, it's very good. You can compare it to experimental data. And so this is not showing that the ClO2 minus is supposed to stable. And you can tell that because the number goes down a very small amount when you go from the -1 to the -2. So it's not a very big amount when you go from the neutral to the -1, or from the +1 to the 0, or from the +2 to the +1. So you have a difference with how much the energy is. Okay?
Well, and the other thing to bear in mind is that this chemistry in the enzyme, of course, occurs in a condensed phase, right? So the question of what charge of the anion is most stable is largely factored in. You want to understand the action.
I thought that was your question at first. That's why I tried to argue the stabilization.
Because in aqueous solution, ClO2 minus would actually be solvated chlorine monoxide.
Right.
Right. So it wouldn't be chlorine. It wouldn't be chlorine 3 anymore. It'd be chlorine 2.
You need somewhere for the electron to come from.
Yeah, I get your point. I get your point. But in the actual reaction, ClO2 minus would be nonsense.
Right. Yes.
So for your
Go ahead.
Let's continue one section.
I was just gonna, so your ClO2 minus, so that should have 2 unpaired electrons, right? Or you have 2 extra electrons in there, so why would your magnetization be 1.
Can you repeat this one more time?
So you have 2 unpaired electrons potentially that you added because ClO2 isn't a neutral.
Let's Braden, ClO2 minus chlorite. Is that an open shell or a closed shell system?
2 minus or 1 minus?
No, 1
1
minus.
minus.
1 minus. They have even number.
It's close.
Single-
It's
single.
close. The anion is close.
Okay, never mind. I see. Well, then for your other magnetizations, though, why are they negative?
This is a very good question. Also a question that I have. That's why also I'm trying to use the non-linear spin to maybe amplify the level of theory.
Well, usually if you don't have the right ground state or if you don't have the right electron configuration, it gives you weird spin numbers. So usually that's an indication that you're not in the ground state.
Well, I guess I don't know how vast does it specifically, but there's no reason why you can't have this negative, right?
Well,
Because it could just be a beta electron.
magnetization is usually just a magnitude. So it should always be positive. Yeah.
So, when you go to your image of the of the formation of the iron-oxygen bond and the breaking of the oxygen-chlorine bond.
Movie?
Yeah, you can play the movie while we chat. That's cute. No, I didn't mean that. So in this process, do you learn anything in the calculated process? Do you learn anything about the nature of that reaction? That is to say, what do the products actually? What are the products? Is that OCl fragment anionic or neutral?
Yeah, so this, I could find the answer to this. So the actual dynamics is done kind of on a low level theory, so it produces a geometry, and you can compute those geometries at a higher level. To figure it, like do a bond analysis, say using Gaussian, like a natural bond analysis, and see exactly where these electrons are kind of sitting between atoms, to see what kind of transfer is happening. That's what I'm thinking. I would be interested in this, say like halfway through when the transfer is happening, you'll have different occupancies of orbitals between electrons, or, between atoms. And so that kind of information, I think, would be really good.
From a mechanistic point of view, that would be, in my view, the most interesting question to answer here. Because I would like to know, is that OCl fragment chlorine 1 or chlorine 2? In other words, is that a homolytic bond cleavage or a heterolytic?
Yep. And at the beginning, I mentioned that we're interested in finding that, so I will find the answer to this.
My other question is this the only productive collision that you were able to find for any orientation of the chloride coming in?
Yeah, so like I said, I only took incoming chloride from a plane, so a vertical plane cutting the macrocycle in half.
So you forced the chloride plane to be collinear with that, or I mean coplanar with that.
Coplanar with that
Yeah.
at different angles of approach. So it can come in the pocket, coming into the pocket of through the enzyme exterior is almost in plane with the macrocycle, a little bit under. And so the chloride has to kind of come up over in order to get to the reaction site. And so where that comes up and over and how that angle of approach is what I kind of tried to model. I assumed that it didn't come over here and approach from a 90 degree away.
Another interesting question would be, can the chloride associate with the iron in an 8-2 fashion?
Yeah, and I did not model those types of interactions. I could.
Because this sort of speaks to the intrinsic reactivity of just the iron porphyrinate and the chloride. It would be interesting to compare and contrast that with what what we know and suspect happens, as you and I have discussed, in the enzyme active site. see how, to sort of think about how the enzyme is actually guiding the reactivity of the substrate. That would be pretty cool.